So this video is about the feature regression model. That's what we're going to do in this video, the feature regression model. And then we're going to extend it to something called the random feature regression model, which is just going to be the feature regression model where some parts of it are chosen randomly. And this model is the simple model that wide neural networks are supposed to behave like. So wide neural networks are complicated, but in this limit, they're supposed to behave like this simple model. So before, we should understand this simple model well, and that's what we're going to do in this video. I'm going to give you the main results about this model. And you might have seen it before in a stats class or something. Maybe you want to skim the notes quickly and you can skip this video, but I'm gonna do the whole thing in details, kind of assuming you haven't seen anything before, because some people haven't. Okay, so what is the model? What are we trying to do here? I'll start by saying what world we're living in. We're living in the supervised training world. So imagine we're doing a supervised learning situation, and I want you to imagine that we have a bunch of test points. So we have x1, x2, all the way up to x and x, where nx is going to be the number of training examples. And these are all going to be vectors in some input space x to the r and in. And in is going to be the dimension of input space. So you can imagine these are pictures or something. So if you had 100 pixel by 100 pixel images, you could encode those in vectors of size 10,000. And these could be the pictures that are given as examples to us. And we're also given some outputs. So y1, y2, all the way to y and x. And these are vectors in R. And so like an example could be you're given pictures of cats and you want to determine how cute the cat is of the picture you were given. So we're given these 100 pixel by 100 pixel images of cats and we want to determine how cute is the cat. We have a bunch of examples and then we would like to come up with a function that works well using this training data on other examples from the internet. So any kind of situation like this where we're trying to go from input to output and the output is a number, this is a regression problem, and we have some training data that makes it a supervised learning problem. So the way we're going to do it is like this. We're going to do something called the feature regression model. What do we do in the feature regression model? Let me scroll down here. So step one, we have to choose some features. Choose some features. So what is a feature? A feature is simply a function, f phi, from Rn to R. And we're going to have many such features, so let's number them. I, 1 less or equal to I, less or equal to n par, where n par is going to be the number of parameters in the model. Let's fit the word parameters in there. Number of parameters in the model. So we're going to have all of these features. Maybe one feature tells you, is it a black cat? Maybe one feature tells you, how big is the cat's nose? So phi I is supposed to represent some feature that is relevant to the problem, and phi I of the input tells you how much of that feature appears or not. So that's the like high level idea of what these features are. We have many of them, so n par is some big number, and we combine them all to make a vector. So you can think of this all together. Phi is going to be some map that goes from R and in to R to the n par. So we stack all the features together in one big vector, n par. Those are the features. Once you have the features, you combine all the features together into one final function. So step two, this is going to be combine the features. And we're going to combine them linearly. Linearly, is that a word? Well, let's pretend it is. Linearly. So that's what makes this model so simple. It's a linear model. The features might be very complicated or non-linear, but when they're combined, that's a linear combination, and that's what makes the whole model very simple. So we're going to combine the features linearly. What do I mean by that? So our output is going to be some function f. Let me write it like this. So f is going to be the output of our model, and it depends on two things. It depends on what you input, like what image you're inputting into it, and it depends on what the parameters are. So x is the input. This is the input from n in, and theta represents all the possible parameters in the problem. So this is the parameters from r to the n par. Okay, and what is f of x theta? Combining all of the features we had linearly. So the way to write that in like algebra notation, linear algebra notation, you do theta transpose times phi of x. And to make sure that everything works out here, I'm going to write down the dimensions of all these vectors. That's written in the notes as well, so if you like that, that'll be there. So this thing should be an n par by 1 vector. Theta is also an n par by 1 vector. It's the vector of all the possible parameters in the model. So when we take its transpose, we get a 1 by n par vector. And if you combine them together, you get a 1 by 1 vector, also known as a number. That's exactly what we want. F inputs something from Rn and outputs a number. This is just an inner product. So another way to write this is like this. The sum from I equals 1 to n par phi theta I, the ith parameter, times phi I of x, the ith feature. So you combine them all into a linear, you combine them linearly and get an output. Okay, there's one other thing that we're going to do here, which might seem weird at first, and I'm going to multiply everything by a constant. And you might think multiplying by a constant doesn't do anything, but it turns out that in the limits we're looking at, multiplying by this constant is going to be very important. And what we're going to do is I'm going to multiply everything by 1 over the square root of n par. 1 over the square root of n par. So that's going to be the definition. And the reason I'm doing this is because I want to look at the limit where the number of parameters in the model gets very, very large. So the number of features we're looking at just gets bigger and bigger and bigger. And in that limit, by dividing by 1 over square root of n par, that's exactly the right type of thing, so that when we add up the sum from I equals 1 to n par, that sum doesn't explode. So if you didn't have this normalization constant in front, then when you added up more and more things, you would get a bigger and bigger number. You would have something that doesn't converge in the limit. But by dividing by 1 over square root of n, it is exactly something that converges in the limit. So that's why I'm putting that in here. I think that's maybe the only part of the game that you might not have seen. If you've taken a statistics class, you've seen this before, but you probably didn't see it with this 1 over square root factor. You might also recognize it from the central limit theorem. So the central limit theorem tells you that if you add up n things, then you should probably divide it by square root of n to make sure that you get something nice in the limit. So the same kind of idea going on here. So that's our model. We have our model. We have our data, our training examples. How do we use the training examples to train the model? So this was, maybe we'll call this step 2a, defining the model. Step 2b is training the model. Step 2b is training the model. So what we're going to do is we're going to define a loss function, and then we're going to try to minimize the loss function. And the loss function tells us how bad are we doing at training, how bad is our function doing at these examples we were given. So the loss function, it depends only on the parameters, and its definition is going to be this. It's going to be 1/2 the sum from I equals 1 to the number of examples of f of xi, the ith example, at these parameters theta minus yi. So if we're right on, we get that perfect, that's a small number. If we're very far from what it's supposed to be, that's a big number. We're going to square these and add them all up. That's going to tell us how bad our parameters are doing. We want to make this loss function small. I'll say one other thing. You can also, as a sum, you can write it like this. It makes perfect sense. You can also write it as a vector. So I'm going to do that, 1/2. You can write it as a norm like this, x theta minus y squared, where x we think of this it's a number of examples by one vector, and it's the vector where you just stack all the examples together. A number of examples by the input dimension, rather. So it's this vector, and applying f to it gives you what you would expect. So f of x theta gives you a number of examples by one vector by doing this, x1 at the parameters theta all the way up to f of x and x theta, and y is the vector with all of the outputs, y1, the training outputs. So the reason to use this notation is it just keeps things compact. So instead of writing a sum here, you write it as a vector. And I'm going to try to do that everywhere in this in these notes, I've tried to keep things as compact as possible by writing things in terms of vectors and matrices and multiplication. So if you like linear algebra, that's good. If you don't, you might not be a huge fan of this, and you might prefer to write it all out with sums. You can totally do that. Okay, so that's the loss function. How do you go from the loss function to training? And the normal way is to do something called gradient descent. Gradient descent. So what is gradient descent? In gradient descent, you have an initial parameter value theta 0, and then you update it. You go theta 0, theta 1, theta 2, theta 3. You update according to this rule. Theta t plus 1 is theta t. And you go down, you move in a direction so that the loss function is decreasing. So that's why it's called gradient descent. You're descending along the gradient. So some learning parameter times the gradient of the loss function. So that's gradient descent. This is in a discrete time. Discrete time, t is 0, 1, 2, and so on. That's the normal thing people do. Computers are fundamentally discrete, so it makes sense to do this. We are going to not do this. So actually, we're going to do something different. And what we're going to do is something called gradient flow. Gradient. And this is just mathematically easier to analyze. And all it is the continuous time version. Continuous time version of gradient descent. So instead of t being 0, 1, 2, 3, and so on, t is going to be a positive number. So t greater than or equal to 0, but it could be 0.1, 0.2. It's a real number now. And the rule is, instead of updating like this by the differences, we're going to update using derivatives. So the rule is the derivative of theta of t. We move down in the direction of the gradient again. So minus alpha times the gradient of L. So this eta learning parameter and this alpha learning parameter are related. They're not exactly the same, because if you want to go from gradient descent to gradient flow, you have to think of taking the step size very small. So just like differences are approximated by derivatives, gradient descent and gradient flow are almost the same thing. It's just mathematically more convenient for us to work with gradient flow. So that's why we're going to do it. It's the same way in when you take calculus courses. A differential equation is somehow not so bad, but a difference equation is very annoying. So that's why we're doing gradient flow. Okay, so what have we done so far? We have our training examples. We have our feature maps. We have our model, which is the linear combination of the feature maps. We have our loss function, and we have defined how the parameters update. And by doing this, you can look at how is the training going over time. So over time, we update by this rule, the gradient flow rule, and then we can ask ourselves, after we're done training, after a long amount of time of going by this gradient flow rule, so question, how are we doing? So in this limit, so limit t goes to infinity of theta of t, that's what happens after we train for a long amount of time. Can we say how well that does? So this limit, let's call this thing theta infinity, if it exists. How are we doing in this limit? So do we fit the training data well? Do we fit? Another question is, how do we do? Do we generalize? Do we generalize well to unseen examples? So those are the questions we want to ask. And we want to know, in this limit, we want to know about theta infinity. And it turns out, all of these things, anything you could possibly want to know about this model, can be answered in terms of a very simple function. So the answer is, how are we doing? All questions can be answered. All questions. Maybe let's say all questions about training, generalization, etc. They can be answered using the kernel function. So what is a kernel? A kernel is a function, and it inputs two things, has two inputs from the input space. So it has two possible inputs and outputs a single number. So k of x prime, where x and x prime are things from the input space. And it's defined as follows. It's going to be 1 over the square root of n par, no square root, 1 over n par times the sum from I equals 1 to n par of the features. Phi I of x, phi I of x prime. So by combining the features together in this way, doing the inner product of the features, you can also write it like this. 1 over n par phi of x transpose phi of x. By doing this inner product, you get this kernel. This kernel has two inputs, and it turns out that everything under the sun can be answered about this model in terms of just this kernel k. So even though it's there's a lot of moving parts in the model, it turns out the only thing that matters at the end of the day is this kernel k. And I'll say one other thing. There's this nice factor of 1 over n par. You might recognize we're dividing by 1 over n par. We're adding up n par things. That's an average. This is an average. This is an average. And in fact, that was exactly why earlier I divided by 1 over square root of n par. That 1 over square root of n par, in the kernel, it translates into just a 1 over n par. And by doing this, we get an average. And averages are nice. And that is why I did that. And that is why the whole model turns out really nice, because we have this nice average. So this kernel k answers all of the questions. So what do I mean by it answers all of the questions? So there's two things the kernel k does. It does double duty. Two things the kernel k does. So thing number one, it does training dynamics. So thing one, this is theorem 6 in the notes. Theorem 6, training dynamics. So I'll paraphrase this. K guides, or maybe let's say K determines the evolution of f of x theta t. So if you want to know what the function is doing, how is the model evolving under this gradient flow, K tells you what it does. I call that training dynamics, and I put that in theorem 6. I'll tell you what it is in a sec. That's the first thing that K does. And the second thing that K does is in proposition 7, which is initial distribution. So K does the training dynamics. K also manages the training distribution, so the initial distribution. So under Gaussian initialization, let's say, so if you initialize the weights in a sort of standard way, K determines the distribution of f at time 0. So K does two things. It tells you how is the thing evolving. So it tells you exactly how things behave in time, and it tells you what happens initially. And if you combine these two things, so if you combine theorem 6 and proposition 7, if you combine them, you know how things are changing, you know how they started, then actually you know everything. So for example, you know, and this is in theorem 9, you get, for example, that the expected value of f of x theta infinity. So if you want to know what happens on average, there's some randomness in the model because the weights will be initialized randomly. But on average, what will happen to any training point, it will depend only on K. Okay, so these are the things that K does. It does the training dynamics, and it tells you about the initial distribution. And if you combine them, you know exactly what the model does. So that's what I mean when I say that this kernel K, it drives the whole bus. It does everything. It's the training dynamics, it's the initial distribution, and you can know everything you want to know about the model using K. So let me tell you what the two theorems say exactly. Theorem 6 and proposition 7. So you can also read along in the notes if you prefer nicely latexed notes to my messy handwriting. So let's see, theorem 6. Okay, so we're under these assumptions, so we're using the gradient flow rule. We're definitely in the gradient flow rule. And so the thing that happens if you do this, the time derivative of f of x theta t, so for some fixed point x in the input space. So the parameters are evolving. If you feed the evolving parameters into the function, you get some number that's evolving. How is that number evolving? And it turns out that the evolution depends only on K. So here's the formula. You might think it's some complicated thing, but it only depends on K. So what is the formula? you get alpha So let me write it down and then I'll explain what it is. Okay, so this is a nx by 1 vector. This is a 1 by nx vector. So you take the kernel k. So first thing you got to do, this thing is just the training examples. So y is the training labels. F of x theta t, remember, is that vector. F of x theta t is this vector of how f is doing on all of the training examples we have. So at time t, you plug in all the training examples into this thing. You get a big vector. Y minus that is the difference between the truth and how our function is doing so far. And so this is sort of like measuring how far we are on the training set. And you take how we're doing on the training set, and you feed it through the function k. You multiply by this 1 by nx row vector kxx. What is that? Kxx. This is the row vector you get by feeding the training examples into the kernel k. So this is k of x, the first training example x1, k of x, the second training example x2, and so on, k of x, the last training example nx. So you make this row vector, and then you just multiply this row vector by this column vector, and you get a number. That tells you how f is evolving. And if you have taken a course on differential equations, you might recognize this is actually a very simple differential equation. So how is f evolving? Well, you do some linear combination of f, but you just multiply it by a constant. So this matrix only depends, k of x. X does not depend on t. So the evolution is very simple. It's just given in terms of this k matrix, and you can solve it. So and I have a video on how to solve this. So you can solve it, and if you solve it, you can get all sorts of answers. But for example, the thing we're interested in is at time infinity. So if you solve it, you get this formula. What happens at time infinity? And in fact, I'm going to write down the difference between time infinity and time 0. So by solving the differential equation, you can figure out how did we change from our initial value. And the answer is just this formula. So k of x training examples, again, this is the 1 by nx row vector. Okay, here is something that is a bit more complicated. K of x inverse. So this is an nx by nx matrix. And it's the matrix you get by plugging all of the training examples into the kernel k. So k of x is equal to this. Let's write it like this. K of xi, xj. And I and j go from 1 to the number of examples. So this is a matrix you get by feeding all of the possible training examples in all possible pairs into the kernel k. And then you have to do its inverse. So all of this is assuming k of xx is invertible. So you do the inverse, and then you multiply by this thing we had before, y minus f of x theta 0. So this is the nx by 1 vector at initialization. So this is really great. This tells you want to know what happens after training. That's this term. What happens after training? Well, you have to know only what happened at the original value, what happened initially, and then you sort of multiply that by this matrix of all the training examples. So this has all the training examples in it. And I think this formula shows you very clearly how the model is evolving. So there's the kernel k, which depended on the features. So k was defined by the features, but that had nothing to do with the training data. And then to get how the training works, all we have to do is take the training examples in this vector x, and we feed it into the kernel k according to this matrix, and this row vector. And once you do that, the evolution of the model, what it does at time infinity after training, is exactly given in terms of this matrix. So there's a really separation of the features that defines k and the training data that just gets fed into k to give you what the function is. So this is sort of like an exact solution of what the training is. So if you have this formula, you can skip the step in your computer program where you run the gradient flow or gradient descent. You can skip that. If you just know how to do matrix multiplication, you can just know what the output is going to be. And in some situations, maybe it's better to do the gradient flow or gradient descent. But in other situations, maybe it's better to really just do it with this matrix K. Okay, so this is theorem 6, the training dynamics. There's one other thing to say in theorem 6 I think that is interesting. You can see what f does. You can also see what the parameters do. And I'm going to write that one down too. So theta infinity minus theta 0. How do the parameters change? And the interesting thing about how the parameters change is how they scale. So there's a factor of 1 over square root of n par in this. So the formula is 1 over square root of n par phi of x. So this is an nx by n par vector. Sorry, the other way around. N par by nx matrix by taking the examples and feeding them into the features phi. Then you multiply again by this k inverse. So this k inverse of xx is the inverse of this matrix. And then you multiply again by y minus f of x theta 0. So initialization again. So you can tell how the parameters are changing during gradient descent. I can give you a formula for what the final values of the parameters are going to be. That depends only on the initialization. So if you tell me what theta 0 is, I can calculate all of this stuff, and I can tell you what the final parameters are going to be. And I think the interesting thing, at least to me, is that there's a factor of 1 over square root of n par in front. And what that means is that as the number of parameters gets bigger and bigger, each individual parameter only has to change by a tiny little bit to get to this limit at infinity. So the final thing is, in this situation, maybe this is worth pointing out as well, that the training data is perfectly fit. So the weights only move by a tiny bit, and nevertheless we still have this this thing that the training data is perfectly fit. So at time infinity, you'll perfectly train the training examples. Okay, so that was what we were calling theorem 6, the training dynamics, which says that if you know k, you can use k to figure out the evolution of f over time. So you can figure out f infinity, how it evolves from its initial value. Proposition 7 tells you that k is actually also involved in the initial distribution. So as long as you're under a Gaussian initialization, so I'll tell you exactly what this means, then actually k will tell you what happens at time 0. So theorem 6 said this is how it's evolving, this is how it changes, and proposition 7 says this is how it starts. And that's a simple theorem as well. So I'm going to show you what that says. Okay, so here we go. Proposition, this is called proposition 7 in the notes. And the initialization is like this. So at time 0, you have to set your weights to something, your initial parameters, and we're going to choose them Gaussian. So assume theta 0 chosen so that all parameters are Gaussian with mean 0 and variance 1. So some people call this a standard Gaussian, but we're gonna, I'll say what it is. So all of the parameters are mean 0 and variance 1, and they're independent. Maybe I should add that. So are independent. So they're independent Gaussians with mean 0 and variance 1. And if you do that, so all the parameters theta are independent Gaussians at time 0, then what is f of x theta 0? Well, we know the formula. The formula is just theta transpose phi of x. So this is a linear combination of these Gaussians of mean 0 and variance 1. And if you know about Gaussians, you know that if you do linear combinations of Gaussians, it's still Gaussians. So the theorem is going to say, or the proposition 7, what does it say? It tells us the distribution of f of x theta 0. So at time 0, f of x theta 0, it's a linear combination of these Gaussians. So this will also be Gaussian. It is also Gaussian. Moreover, I can tell you its mean and variance. The expected value of f of x theta 0 is 0, and its variance, okay, this is where things get a little spooky. Like, I told you that k appears in both of them, but the variance is k of xx. So that kernel k, if you do k of xx, that gives you the variance of the point f of x theta 0. So that's a nice thing. If you start with Gaussians, you start with Gaussian weights, then the function f is also Gaussian. That's what proposition 7 says. And it's true not just for a single point, so this is for any single point, but you could also make a vector. So that's also for any set x1 all the way up to xn test. So if you have a set of test points, you try a whole bunch of points, maybe you want 3 points you're interested in. Not only is it true that each point individually is a Gaussian, but altogether they make a Gaussian vector. So f of x test theta 0. So this is the vector f of x1 test theta 0, f of x n test theta 0. This vector is also Gaussian. It's a Gaussian vector. Okay, it's Gaussian vector, so I have to tell you its mean. Its mean is 0 again. So this is a vector now in Rn test, but its mean 0. And okay, so Gaussian numbers have a variance. Gaussian vectors, okay, you can't talk about the vector or the variance of a vector, but you can talk about the covariance matrix. So I'm going to write that with cov. So this is the covariance matrix. So this is an n test by n test matrix. And this matrix is again given by the kernel k. So you do k of, what you do is you do k of x test. So this is an n test by n test matrix. And if you want, I can write it out. It's this matrix, k of xi test, xj test. Ij go from 1 to n test. So not only is it true that every point is Gaussian, but any finite collection of points is jointly Gaussian, and its covariance is exactly the kernel k. That's what proposition 7 says. So let's scroll back up to the high-level picture. Theorem 6 told us that k was in charge of the evolution of the model. So k tells you how you get from the initialization to your final destination. Proposition 7 says that actually on initialization, the kernel k tells you what initialization was too. And if you combine Theorem 6 and Proposition 7, you combine them, you get Theorem 9 that tells you that actually the whole model only depends on k. So I'm going to write down what Theorem 9 says now. So Proposition 7 is some kind of statement about Gaussians. And Theorem 9, and you can make lots of versions of Theorem 9. My version is going to be this. So the expected value of f of x theta infinity. So, okay, look, this was theta 0. That was proposition 7. What happens at initialization? Theorem 9 is what happens at time infinity. So at time infinity, the expected value is equal to this, k of x, k of x inverse times y. And this is assuming Gaussian initialization. Okay, so if you start with the Gaussian initialization, you end up with this. Okay, not only that, but I can tell you what the variance is going to be. So the variance of f of x theta infinity, it's equal to this. It's k of x, lowercase x, minus, and then you do this funny inner product, k of x, k of big X inverse k of x. That's the variance. So this model is random because the initialization is random, but for any individual point, I can tell you on average where does it go at time infinity. So this is after training, and I can tell you the variance. And so you can use this to figure out, like, you know, if you know the kernel k, now you know everything about the model. You know how well it's going to work for unseen points. You can use this to measure generalization error, anything you want, anything like that. I'll say one last thing, and the last thing is exactly because of this miracle. So there were two things that the kernel did. It did the training dynamics, Theorem 6, and it also told us the initial distribution. And because both of those things were the same, it ends up being, there's this miracle that happens. which is in theorem 9, these formulas are both true, but not only that, also, because of these two formulas, you can interpret f in a certain way. So f of x at time infinity, theta infinity, it has the property, it has the following interpretation, is the same, it's the same distribution as f of x theta 0. So at time infinity, after training, it's the same as the initialization conditioned on the event that f of xi theta 0 equals yi for all examples. So if you take the initial distribution, that's some crazy, big function, Gaussian function. If you condition it that all the training examples are perfectly fit, then you get the final distribution. So the final distribution is the original distribution, but conditioned to fit the training examples perfectly. So I think that's a really nice theorem that helps you understand what is the network doing. The network is updating the weights to fit the training examples better and better, and at the end of the day, you get a Gaussian, which is the original thing conditioned on that perfect training event. Okay, so that is the high-level overview of the feature regression model. And I'm going to have a separate video where I prove these things. So they're not hard proofs. Like, for example, the proof of theorem 6 is something from a differential equations class, like a second-year differential equations class. Proposition 7 is something from like a first course in statistics or probability. None of these things are hard. And when you combine them, you get the perfect solution to this regression model. So there'll be a video on that. And there'll be a second video where I talk about the random feature regression model, which is what happens if you choose the features phi I. Instead of choosing them deterministically, what if you choose them randomly? So something happens that's nice there too.